Hello and welcome back to BITLearn. This is where I break down complex technology from years of my product building experience into simple, powerful lessons. Because once you really understand the fundamentals, you can build anything apps, products, your own startups, anything is possible. With that, let's get started with episode 5 of our electronics series. We are stepping behind the curtains of modern computing today to see how some of the simplest ideas end up powering the most complex machines ever built. You will discover in the next few minutes computers are not magical, they are clever and extremely clever. If you have missed any of the previous episodes about transistors, gates, about how NPN, PNP works, what are semiconductors, any of the basics of electronics, do check out the previous episodes. But for now, we'll continue with the computer's cleverest trick. That is this episode. This episode is about those clever ideas, how computers subtract without subtractors. Yes, that's correct. How shifting bits becomes multiplications. They're kind of cheating, aren't they? How one type of logic gate can build an entire processor. It's just one type. And how Boolean algebra quietly governs everything underneath. Let's get started. The first one, why subtraction is a problem. When early engineers designed the first computers, addition was very straightforward. Adding bits is mechanical, just handle the carries and move on. But subtraction, that's a different beast. That introduced complications. You need borrowing, you need to borrow bits, you need to handle sign, you need extra circuitry that behaves differently depending on the input. So instead of adding complexity, the engineers came up with a clever idea. They flipped the question. Do we really need a subtraction circuit at all? Is the question they asked. This way of thinking, looking for simplification instead of building more, gave birth to one of the greatest tricks in computer science. A trick that is so effective that every CPU today still relies on it. The trick is turning subtraction into a form of addition. How does that work? Let's see. Let's start looking at the idea of a 2's complement. 2's complement is beautifully simple once you see it. Instead of teaching the computer how to subtract, we teach it how to turn a number into its negative. And then we just add it. Sounds simple, right? To get the negative of a number, just invert all the bits and add a 1. So here is a very tiny example. 3 is represented in binary as 0, 1, 1. The first bit is 1, the second bit is 2. So you add it together, you get 3. So 3 in binary is 0, 1, 1. If I had to invert the bits, this would become 1, 0, 0. And if I add a 1 to that, this becomes 1, 0, 1, which basically is negative 3 or minus 3. So in 3, this is a 2's complement of 3. Now let's look at how subtraction works. So a minus b is basically the same as a plus the negative of b. You are still doing an addition, but you are doing the negative of b. So all we had to do was come up with the complement, 2's complement of the number, create the negative number, then add it. So only addition hardware is needed. No complicated borrow logic, no special cases, no separate design for positive and negative numbers, nothing. 2's complement is more than a representation. It's a kind of a simplification philosophy. So it makes hardware really smaller, faster, cleaner, all those things. And because the representation wraps around very naturally, the final carry can simply be thrown away. So the result, computers do billions of subtractions per second without ever actually doing any subtraction. It's all addition and doing the negative number addition. So now let's look at another concept called shifting, shifts. The fastest way to multiply and divide is to shift. What is that? So this is a very elegant idea. Binary numbers are so positional, right? If you have 101, you basically have bits representing a decimal number in a certain position. So moving the bits left or right naturally changes their values. So if you have a set of 4 bits, all of them 1, if you do a left shift, that actually multiplies the number powers by 2. If you do a right shift, that divides the powers by 2. Go ahead, try it out. Write a binary number, maybe a 4-digit, 4 position binary number, maybe 1010. Try shifting it to the right. You are basically dividing it. Try shifting it to the left. You are basically multiplying it. So shift of 5 left by 1 gives you 1010, which is 10. Instant multiplication. So shift operations are so cheap for the CPU that compilers often replace very heavy multiplication or division with simple shifts whenever possible. Again, Computing prefers simple things done well over doing complex things directly. So then here is the fourth concept. We talked about subtraction without doing any subtraction. We talked about doing multiplication and division without actually doing any multiplication or division. We were doing left shift and right shift. Now let us talk about a universal gate, the surprising power of a NAND and a NOR gate. As we go deeper into hardware, imagine you had to build a giant machine, but someone told you you're only allowed one type of building block. So it's like building a house, but you're allowed to build only one type of building block, which is a brick. Can you build the entire house with the brick? Yes, you can. You just need lots of copies of those bricks. It's not impossible, right? But in digital logic, it works beautifully. NAND and NOR are called the universal gates because any other gate and or not XOR, all of them can be built entirely from NAND and NOR. So this discovery kind of changed hardware design forever. Why? Because if you can fabricate one type of gate reliably, if you have looked at the transistor example from our previous episodes, you know that we can build a NOT gate from just a transistor because a transistor can switch from on to off state. It can also control the current, which means you can also use it to build a NOT gate. So just because you can fabricate one type of gate reliably, you can construct an entire processor out of it. Manufacturing becomes simpler, circuits become more predictable, and it's much easier to manufacture. The beauty is in the simplicity. A vast, complex digital system can rise from a single repeating structure, just like how nature builds infinite variations out of our DNA's four letters, right? Entire DNA is constructed from four letters. You get so many variations out of it. Very similar to that. So we covered four topics which are very fundamental to building simple computation using electronics. The first one was about subtraction without actually doing any subtraction. The second was using 2's complement and using left shift and right shift to multiply and divide. Then we talked about a universal gate, the NAND and NOR gate, which can be used to construct all other Boolean gates like AND, OR, NOT, XOR, those things. Now that we have all the pieces together, let's look at what Boolean algebra can do for us, the mathematics of logic. Behind all behind all these gates and circuits is a mathematical framework created by George Boole in 1854. Boolean algebra takes the messy world of logic, if then, if else, all of those things, and it gives it very clean, consistent rules. Boolean algebra is a set of rules. So every value is either 0 or 1. Just like our binary bits, the Boolean algebra also assumes that every value can be either 0 or 1. And every operation is one of AND or not. So with these, we can express any logical condition, simplify a huge expression, shrink giant circuits into elegant ones. So Boolean laws, basically commutative, associative, distributive, they look very familiar from regular algebra, but they behave differently because the values are truth values, not numbers. So something like a truth table where you have 1 plus 1 equals 1, 1 into 0 is always 0, 0 into 1 is always 0 again, things like that. So these aren't just academic curiosities. They basically let engineers remove unnecessary gates, reduce power consumption, speed up circuits, and basically use very simple building blocks to build something very complex. So the huge computer that we use today with all the fancy AI logic is actually built on very, very simple things and with also a few clever ideas. So Boolean algebra is the quiet language of all digital logic. Something to remember formally as part of Boolean algebra is the DeMorgan's theorem. This is the bridge between math and hardware. So two more rules just to complete the picture are DeMorgan's theorems. A plus B naught is equal to A naught into B naught. So similarly, A into B naught is the same as A naught plus B naught. This show how and, or, and not transform into each other. They are the reason NAND and NOR gates work as universal gates. So every time a designer replaces a chunk of logic with NANDs or NORs, they are using De Morgan's theorem. Okay, so I will not go into too much details. You should check out a textbook to really understand how this theorem actually works. But it's just enough for you to understand that this is the bridge between math and hardware. So let's put it all together to wrap up this episode very, very quickly. So when you step back, you see a remarkable pattern. 2's complement turns subtraction into addition. Shifts can perform instant multiplication and division. Universal gates, they simplify the building of the entire system. Boolean algebra gives us very clear structure and rules, and DeMorgan's theorem ties everything into one coherent design language. This combination of mathematics, clever engineering is what makes computers really powerful. There is no brute force, there is no complexity, but we simplify everything to the smallest possible component, but very simple rules. We stack it intelligently, and we get a very complex system out of it. So, computers don't succeed because they do everything. They succeed because they do a very few things incredibly well. And let those few things scale infinitely, you get a very complex system. You could apply it in real life as well. You don't need to succeed in everything that you do, but make sure that you succeed in a few things you do incredibly well, and basically scale those things to a large number. You will be extremely successful. So, just to close out quickly, that's episode 5. You now understand the core ideas that quietly drive every device you use. If you enjoyed this journey into the foundations of computing, do like the video, subscribe to the channel, share it with anyone who's learning computer science or electronics. This is BitLearn. So, come back for more, and thank you very much for watching. I hope to catch you in the next episode.